All right, welcome back, everyone. So now we're going to discuss existence and the uniqueness theorem for first-order linear differential equations. Let me show you what the theorem is, and then we can just do a few examples on that. Here you go. So let's suppose you have a linear differential equation of this form. So this is what we're looking at. So if the functions p and g are continuous on some open interval I containing the initial point to, then there exists a unique solution or a unique function phi such that will satisfy this differential equation. So the big picture here is that if we can determine where these guys are continuous, containing that initial point on that interval, we're certain to have a solution. Moreover, that solution is unique. So that's really the big idea of this theorem. Let me show you some example to see how this could be applied. All right, so here are the examples we're going to work out where we can apply this theorem to kind of tell us there exists a solution and that solution would be unique. So it's kind of a nice way to analyze the problem without even solving the problem or without solving for the solution. So first two problem, as you can see, they're same differential equation, except we're imposing different initial conditions. Here your TO is 1, here your TO is -1. So let me show you how this works. First thing you want to do is express each equation in linear standard form. So the linear standard form, we want to have y prime plus some function of p of t times y is equal to another function of t. So I'm going to go ahead and divide all of these, both sides of that equation by t, so that way we have the standard form for that particular equation. So we'll have y prime plus 2 over t times y is equal to 4t squared over t, which will simplify to simply 4t. All right, so now that we have our equation expressed in linear standard form, now we can start plugging in, or we can start looking at where these guys are continuous. So this function right here, this is your p of t. So we'll find the domain of p of t, and this function right here is what we're going to call it g of t. So let's check that out. So we know p of t happens to be 2 over t. So what is on which interval is this continuous? Well, let's take a look at the domain. So the domain of this function, now since t is on the denominator, we want to make sure it's not 0. So it will be everything except 0. So we have -infinity to 0, union 0 to infinity. So that's the domain, that's where it is continuous. For g of t, that's a nice polynomial for t. It seems to be continuous everywhere. So the domain would be the entire real line, -infinity to infinity. Now together, they happen to be continuous on this interval right here, because that's the one that has restriction. G of t doesn't have restriction. So we can think of the interval of continuity happens to be everything but 0. So 0, you have an open circle. Everything to the left and right seems to be fine. So that's one way you can picture the continuity of both of these together. Now let's see, where do we contain the initial point? So for the first problem, we're looking at the initial condition of y of 1 equals 2. So TO is 1. So since TO is 1, so the initial condition of y of 1 is 2. TO is 1, and 1 is contained on this interval. So that means we're going to have a unique solution on that interval. So TO equals 1 is contained on the interval from 0 to infinity. So therefore, we'll have a unique solution on the interval from 0 to infinity. So that's really how you figure out when or where do we have that solution. When it exists, it's unique. All right, now the second part of this problem, we have the same differential equation, so I can still consider these domain for that same problem, but now we're switching the initial condition to be y of -1 equals to 2. So that means for the second part, our initial condition has been switched to a negative value for TO. So we know now TO is -1, which means this value will be in this interval. That means that's where we're going to have our unique solution. So this would imply that we'll have a unique solution for this particular initial condition on the interval -infinity to 0. So I hope that makes sense how you're figuring this out. Now let's take a look at the last part of this problem. So for part C, we have a different differential equation, linear first order, and we want to know where does the solution exist, and we also know that it's going to be unique. So we're going to figure that out after we finish computing their domains. So it's already written in linear standard form, so we know that that's going to be checked. So now this function right here, we're calling that P of t, and this function right here, we're going to call it G of t. So P of t is tangent of t. So if you, I hope you remember the domain of tangent of t. So we know that the domain or tangent seems to be continuous everywhere except every odd integer multiple of pi over 2. So one interval you can look at is negative pi over 2 to pi over 2. You can also look at pi over 2 to 3 pi over 2, and so on. So those are the domains of this function. Then for g of t, we have sine of t. Well, sine, we know it's a nice continuous wave, so the domain for sine is going to be from negative infinity to infinity. So that means together they're going to be continuous on this interval, because that's the one with restriction. This one seems to be fine everywhere. All right, so now on which interval do we contain TO? So TO seems to be, so this number right here, pi, that's your TO. It is contained in this interval. So TO is right there, pi is inside that interval, which means we'll have unique solution on the interval pi over 2 to 3 pi over 2, since that's the interval where our function seems to be continuous and also contains the initial point. All right, that's really it. So the big idea, we have broken it down into a couple of examples. I hope you enjoyed. I'll see you next time. Take care, everyone.